this one's going to be a function within a function within a function. In other words, it's going to go 3 levels down. We're given f, we're given g, we're given h, and we're asked to find f of g of h. So like up at the top where it says f and then the little circle and then g and then the little circle and then h, that's another way of saying f of g of h. In other words, h is inside of g, which is inside of f. Now I use the analogy when we're talking about functions of a factory, right? And I've talked with you guys before about the notion of inputs and outputs, right? And this is no different here with our discussion of a composite function. It's just when we think about a factory inside of another factory, that's kind of what we're the analogy that we would use here. I've been following a company for the last 5 or 6 years called Boston Dynamics. Anybody ever heard of Boston Dynamics? Right? They make robots. You might have seen like the little yellow robot dog looking thing called Spot. Okay, if you're familiar with that, that's the company Boston Dynamics. Really in the world of robotics, they've got robots that can open doors. They've got robots that can run. They've got all kinds of neat applications. They've got robots that can lift boxes and move boxes and things. And so anyway, this company I wanted to invest in, so I was doing some research, like who owns Boston Dynamics, and it used to be owned by a company over in Asia, and I forget the name of them, but more recently they were bought by Hyundai Corporation. Okay, Hyundai, the car maker, right? With the hopes that they'll be able to make driverless cars, right? And so imagine that you've got like this Hyundai factory, right? And here's the big old Hyundai factory. And inside that factory is a little Boston Dynamics, Spot the robot. We're building robot driving or car driving robot dogs. And that's kind of what we have. There's an input that's coming in, bless you. There's an input coming in to this Boston Dynamics little factory. And then when it spits out its robot, that robot goes into, whatever other operation is being done in the larger corporation. So it's literally a factory inside of another factory, for example. So for us, what we're looking at here is we're looking at, all right, h, my h function, what is that? It's square root of x plus 1. Square root of x plus 1 is going to be inside of the g function. Now the g function being 3 over x, now instead of 3 over x, it's going to be 3 over square root of x plus 1. That's g of h. And g of h is going to be inside of, so now that is going to be inside of the f function, and the f function says 2 times your input plus 5. So we now have 2 times our input plus 5. So it's a function inside of another function inside of another function. Okay, what's the innermost function? H, which is square root of x plus 1. It's inside there. And then we move out a layer, and then we move out a layer again. And the reason that this is of importance for you guys is that we're going to be talking today about the notion of an inverse function. In other words, when you put a special function inside of another special function and they undo each other, those are called inverses, right? Like plus 5, minus 5, or times 2, divide by 2, that type of thing. A little bit later on in your math careers, you guys will take calculus and you'll study something called the chain rule. You'll study integration by substitution, and all over the place in those lessons, this sort of notion comes up. My seniors are doing that right now, as far as having a function inside of another function, right? Now, let me get you to try one here. I wonder if you would try, let's do g of f of h. All right, so again, we're putting h on the inside, but this time we're doing h is inside of f, and then that is inside of g. So switching the order up just a little bit. So h is inside of f, and then that is inside of g. Give you about another 15 seconds. Coach Cannon and his superhero music out there is distracting. We got Coach Luckett, Brad Luckett, the younger Luckett, dressed up as Thor. We've got Dr. Brummer is going to be dressed up as Captain America. He's got the shield and everything. Brother Mark is Batman. Let's see who else we've got. He asked me to be the Flash, but I'm teaching you guys, so I said no thanks. And then they've got one other good costume. I forget what it is. Do it. So Spider-Man was out there. I don't know who he's got to be Spider-Man. Look like a student. We've had teachers before. When I first started here, I was 21, maybe 22, and I had to grow a beard so that the seniors wouldn't think I was one of them. Hey, what'd you guys get for this, by the way? All right, so if it sort of might be helpful to consider, what is my outside function? It's 3 over something, and so that's like the large scale, like the macro level. The outside most function is 3 divided by something. Now, normally it would just be 3 over x, but Tiago, what do you have? 3 over what?
3 times the square root of x plus 5.
Beautiful. Beautiful. A function within a function within a function. In other words, we put h of x, we put the square root function inside this linear function f of x, and then we put that inside of this rational function 3 over x. So as far as exercising goes, we can have composition of functions for days, and it's just one level down, one level down, one level down. Now, similar example, except here's something interesting. There's an interesting little twist here. So you and I, let's work on finding f of g. Okay, so we'll do f of g here in blue. F function says 7 times my input minus 10. All right, and my input in this case is g, which g is given to me as 1/7 x plus 10 sevenths. Now, in the previous examples, we were not able to sort of manipulate or work with or simplify down any further our expressions, like what Tiago just gave me. Right? I'm really not able to do much else with that. I guess I could rationalize the denominator, but that would be, really unnecessary. Not really anything else we could do. In this example, I could most definitely use the distributive property, right? What happens when I distribute 7? What's 7 times 1/7? So I got 1x, and 7 times 10 sevenths. So I got 1x plus 10, and then minus 10 at the end. And it boils down to x. In other words, those operators have canceled each other out. The g function had the operator of divide everything by 7, add 10. The f function had multiply by 7 and subtract 10. Those are inverse operations. They undo each other, and it boiled down to x. Tiago.
So you have in the top, it says that f of x equals x. So
There's an implied multiplication being done there, right? And so if we're saying the f rule is 7 times x, okay, so like what would f of 3 be? It'd be 7 times 3 minus 10. What would f of 11 be? 7 times 11 minus 10, right? F of Coach Morgan. 7 times Coach Morgan minus 10. F of G is 7 times G minus 10. And that G function is given to us as this binomial. Okay. Perhaps I didn't let you ask your question fully. Go ahead, Tiago.
no, I just
Have I helped? Okay. So our F rule, our outermost sort of like macro level rule is to say, hey, whatever's in this parentheses, whatever is in this parentheses, in this case it's G, but you're going to multiply it 7 times that minus 10, and then let the chips fall where they may. And so we do 7 times that binomial minus 10, and we shuffle everything out, we distribute, simplify, and it all boils down to x. Lewis.
I feel like f of x is that f.
What do you mean by that?
Like, why is there a parentheses x?
For functions in general? All right, so that's a good question. When we talk about functions, there's really 3 things that this sort of nomenclature or this symbol gives us, right? 1/7 x minus 10. Let's just say that. I can't remember. What is it? 7x minus 10. Good grief. Y'all see how bad my memory is all of a sudden? 7x minus 10. Okay, so there's three things. The first thing is that f is the name of the function, right? We name the relationship. We just say, hey, this function's named f, this function is named g, this function is named h, whatever. You pick a name and you say, this is what I'm naming my function. In the parentheses is my input variable. In other words, we are going to have a rule that is based upon this particular letter. That's my input. We would call it my independent variable. Together, f of x is synonymous with oftentimes y, or our output. Okay, so a lot of times you'll see me swap out, instead of f of x, you'll see me put a y value right there. Okay, and then over here, this is our rule. This is the third thing that we get. This is our rule by which the function is defined. So for example, okay, so like let's say Lewis goes into business producing cell phones, okay? So Lewis has a particular cost function that depends on the number of cell phones that he produces each month, right? I've just named the function C because it stands for cost, and I've said that the cost, in other words, the output, how much money he owes to his suppliers, depends upon N. So the output, our dependent variable, depends upon the input, in this case, our independent variable of N. And then we got some rule, maybe, you've got let's say you've got a monthly cost of $500 to rent your facility, and then let's say it costs you, $200 per cell phone, right? So that's your monthly cost, let's just say. I don't know, I'm making something simple up. All right, so now you've got yourself a name, a variable, and a rule, and you've got your function properly defined. Now, let's say somebody comes to you and says, how much would it cost you to produce 17,000 cell phones or whatever? All you would have to do is you would say, okay, well, what's C of 17,000? And all of a sudden you say, oh, I've got that number right here, 17,000 plus 500. So like, let's say the month of April, you produce 17,000 cell phones, and then all of a sudden, there you go, you've got your cost for that month. Okay, so that's kind of what we're talking about here. And instead of just plugging in a simple variable, sometimes you're called to plug in something else. Okay, like let's say that you went a level down and you said, well, really the number of cell phones that I produce in a given month is not in and of itself an independent variable. Perhaps it depends upon something else. Perhaps it depends upon the price of what are they shortage of right now? You guys follow the news? Yeah, computer chips, processor chips. What did you say, Jack? Ketchup packets. Okay, are they really?
I think so. Because of the amount of
That's not funny, but that's interesting, I guess. All right, but anyway, like let's say your number of cell phones that you produce in a given month depends upon how many processor chips you can pick up. Okay, so now you've got N as a function of P. The number of cell phones that Lewis's company can produce depends upon the number of processor chips that he can get access to. Okay, and let's say, I don't know, we'll make something up, like let's say one cell phone requires 3 processor chips. Okay, so so the number of cell phones equals 1/3 times the number of processor chips that you get your hands on. I don't know how many processor chips are in a cell phone. Maybe just one. I'm making something silly up. So then the idea is that, oh, you know what? We're going to replace this N with N of P, and so now instead of 200 times just a simple N, it's going to be 200 times 1/3 P, and then all of a sudden we've got a function inside of another function, to where now Lewis's cell phone production costs depend upon another function, and that other function depends upon something else, and so that's where this sort of nomenclature comes into play. So have I helped answer what you were asking about? All right. Why don't you guys find for me G of F now? Okay, you've done one already, did a good job on it. Now I want you to find G of F. We'll do G of F in red. And again, this is where we are taking the F function And we are putting it inside of the g function. So we're going to take 7x minus 10, and that's going to be our input for g of x. Jack reminded me of one of the scenes, one of my favorite scenes from an Adam Sandler movie called Big Daddy. Y'all seen Big Daddy before? Anybody?
Yeah.
Adam Sandler is in charge of a kid, and he should definitely not be in charge of a kid. So he pretty much, it's a comedy, and he pretty much learns to take care of this kid. But early on in the movie, he's just letting the kid do whatever he wants to. And so the kid's like, I want to be called Frankenstein. And so he's like, all right, your name is Frankenstein now. This is easy. And then they're walking by a hot dog vendor, and he's like, all right, kid, it's time for lunch. What do you want? He's like, 30 packets of ketchup. And so he's like, all right, get the kid 30 packets of ketchup. So he ate 30 packets of ketchup for lunch and then barfed on the sidewalk, which was gross. All right, let's see here. Charlie, you got an answer for me? We got g of f of x here. What do we get? And walk me through the process. All right, so hold on. The function g says whatever's in the parentheses right here, we're going to say 1/7 times that, and then add 10/7. And so you've told me that f is in the parentheses right there. So what do we got? 1/7 times. Very good. The quantity 7x minus 10. All right, let's throw it to Grove. Grove, where do I go from there? So 1/7 times 7. All right, and 1/7 times 10. All right, and then Paul, what happens after that? Leaving us with x. Now this is a very unique occurrence. All right, what just happened didn't just happen by coincidence. Okay, like I wrote this example up so that would happen. The reason that we see everything boil down to x is because these two functions share a very special relationship. Okay, these functions are known as inverses. They are inverses of one another. Okay, in other words, if I put f inside of g, it cancels out all the operations and you're left with just x. If I put g inside of f, similarly, everything boils down, everything cancels out. These functions are known as inverses. And in fact, what I've got in this red box right here is called the definition of inverse functions. If that phenomenon happens, what we just saw, then those two functions are inverses. And if those two functions are inverses, then we are guaranteed that that phenomenon will occur. It's an if and only if statement. We've talked before about that. IFF means it's a two-way street. So if two functions are inverses, then their composites will both equal x. And you could also say it in reverse. You could say if you have two functions whose composites equal x, then you know those two functions are inverses. Now, why is it helpful for me to know about inverse functions? Well, fellas, we've been using inverse functions all year long, right? You first learned how to solve basic linear equations by doing inverse functions, right? Like I said, x plus 2 equals 7. And you walked in here day number 1 and you told me, oh, that's simple. Subtract 2 from both sides. Use an inverse operation. And that's how you get your answer of x equals 5. Okay? That's because adding and subtracting are inverse operations. And you might be thinking, okay, this is great. Why are you teaching us about inverse operations if we already know about inverse operations? Well, Can we name all of the pairs of inverse operations that we have at our disposal at this point for equation solving purposes? I just illustrated, for example, adding and subtracting. Okay, so what else? Read. Multiplication and division. Very good. Jake? Squaring and square rooting. Excellent. And we're out. Okay, so like that's all we know so far. Add, subtract, multiply, divide, square, square root. But there are a bunch more. For example, suppose I told you the following equation needs to be solved. How would you solve that equation? Take the square root of both sides. Okay. Now what? All right, square root of 9 I could do, but I can't do square root of 3 to the x. Oh, come on. Somebody knows the solution. Quentin, do you know what the solution to this equation is? Yeah. Now, what Quentin has just done is he's used inspection to notice that, hey, look, 3 to the x equals 3 to the 2, therefore x must equal 2. We can eyeball it, and we can solve an equation like this, right? Everybody feel comfy saying, oh, yeah, x equals 2, Coach Morgan. Duh. I knew that. Right? You guys feel that way? Okay. So now what? Okay. That equation has a solution. We just don't know how to find it yet because we don't have an louder. We don't have an inverse operation to undo exponentiation. Now, what Lewis was thinking about was he was thinking about, oh, I know how to undo like power, right? So like if this was like x to the 5th equals 100, we can say, well, coach, just take the 5th root of both sides. What is the difference between those two equations? Here, the variable is in the base, and over here, the variable is in the exponent. So over the next couple of weeks, we're going to talk about a new pair of inverse operations that involve exponents. Paul? Yes, we will in just a moment. So the notion here, fellas, is that we got to add, subtract, we got multiply, divide, we got square and square roots, cube and cube roots, and all that good stuff. But we're gonna expand our horizon now and learn some more inverse operations. But to do that, we first have to understand the notions that we're outlining in today's lesson and in Thursday's lesson. All right. So Paul asked me to come back here. So this is our definition of inverse functions. There's a couple of vocab words in green. All right. The word invertible simply means, oh, this has an inverse. I can find its inverse. Okay. Something that is not invertible has no inverse and is therefore called singular. If a function is singular, then it has no inverse. If something is invertible, it means we can find its inverse. All right. And then down here, a function that is invertible is a function that is called, quote, one-to-one. Write that phrase down. And I'll be honest, this phrase used to confuse the stew out of me. I had no clue, even though my teachers were trying their best to teach it to me. I just did not understand what one-to-one meant. Okay? So I'm going to give you a little illustration of what one-to-one does not mean to start with. Okay? Number one, I want you to think about birthdays. Birthdays is a function, right? Every person has exactly one birthday. That's the definition of a function, isn't it? Every input, every x value matches with exactly one output, exactly one y value. So every person in this room has how many birthdays? Exactly one birthday. But does every one birthday have exactly one person? No. You might share a birthday. For example, my father-in-law and my sister-in-law share a birthday. Now, that doesn't all of a sudden make the birthday function not a function. It just means that that birthday function is not a one-to-one function. One-to-one means that not only does every input have exactly one output, but every output has exactly one matching input. And if a function is not one-to-one, then it is not invertible. Okay, if a function is not one-to-one, it's not invertible. I've got a quadratic graph up here. What do we call the graph of a quadratic function? A parabola. Good. In black up here, I've got a parabola that's sketched out. A parabola is not going to pass my horizontal, HLT, my horizontal line test, right? Therefore, a quadratic function is not one-to-one. And therefore, in its form right there, it's not invertible. So like I can't find the inverse of y equals x squared, for example. Okay. Now there are some workarounds that you and I will discuss, but looking at this picture, what this means is that this one output, this one y value that's right here wherever this horizontal line is, okay, it hits the curve in two spots, which means that that one output has two corresponding inputs. Therefore, that function is not considered one-to-one, and if it's not one-to-one, then it's not invertible, and if it's not invertible, it doesn't have an inverse. Okay, so it's all tied together. So this notion of being able to find an inverse is important. Okay, you go back to my little example over here, 3 to the x equals 5. You don't know how to graph this just yet, but I'll let the cat out of the bag. The graph of 3 to the x looks like this. Okay, that's what the graph of y equals 3 to the x looks like. Okay, is that function one-to-one? Does it pass the horizontal line test? Sure it does. Even over here on this part to the left, what's it continually doing? As we go to the left, it's getting closer and closer to the what? X-axis. It won't ever get there, but it's getting it's behaving asymptotically, which means it's approaching infinitely closer. I could get in my Honda Accord and drive a mile down the road and get out and look, and I get a microscope and see, hey, here's the curve and here's the x-axis, right? So this passes my horizontal line test. Therefore, this function is one-to-one, and therefore it is invertible. And because it's invertible, I will have a way of solving for the exponent, the variable that's in the exponent. Okay, but we're not there just yet. Illustrated the point, though. So we talked about the definition of inverse functions. Let's practice finding an inverse, okay? So I'm going to give you an example here. This will probably be our last thing we do today. I'm going to give you an example here. F of x equals 2x minus 3, okay? Luke, what type of function is that? Very good. That is a linear function, okay? A linear function is invertible, okay? A linear function is invertible. So the way that we're going to find its inverse is that we're going to follow these two steps over on the right. Remember, anytime I put something in a red box with stars on it, you're like, ooh, I should probably write that down. All right, so these are our two steps. What we're going to do is we're going to find the inverse. And by the way, the notation for inverse, I don't want to bypass this, but we're running out of time. This is not f to the negative 1. That's not a power. That's a symbol, a notation, right? It's like when you see the chemical symbol for water. What's the chemical symbol for water? H2O. We're not squaring that H. That's not like some math operation. That is just a notation, a way of saying, hey, there's two hydrogen molecules, or atoms, excuse me. All right, so the first step says switch x and y, okay? But you look at your function, you're like, I don't see a y there. What did we say earlier is synonymous with y? Fx. Good. So it starts out, this function is y equals 2x minus 3. Let's switch x and y then. Wherever there's a y, put an x, and wherever there's an x, put a y. Okay? So now all of a sudden this becomes x equals 2y minus 3. Okay, fabulous. Step 1 complete. Now step 2, we want to solve for that new y. We want to get the new y by itself. Okay, so Will, what would your two steps be to get that new y by itself? So x plus 3 divided by 2 equals y. And so we have now just found the inverse function. So x plus 3 divided by 2. And it's just that simple. Okay, finding an inverse is just that simple. Switch x and y, solve for the new y. Okay. Now that's easier said than done sometimes, as I mentioned, right? So like right now, you don't know, like if I wrote y equals that function we were talking about earlier, 3 to the x, and I said, okay, find its inverse. And you're like, okay, let me switch x and y. So I've got x equals 3y. And then all of a sudden, step 2 becomes much more challenging, doesn't it? It's like, how do I solve for that? How do I get that y out of the exponent? So we're going to talk about that over the next week or two. Okay? But our time is up. So I must bid you adieu. Have a wonderful day. Live Jesus in our hearts. I appreciate y'all's work. Take care. See you guys.